Hello, thanks for joining. This presentation is part of our Impact Center training program, and we'd love to have you visit our facility for a full hands-on training course when we open back up. But for now, Neil Systems has decided to offer shortened online versions of these courses, and we hope that you find them beneficial. My name is John Lamp. I'm a technical engineer at Neil Systems, technical lead here at Neil Systems, where I've worked for 9 years. This presentation is the second of a two-part series, and today we'll continue where we left off. If you remember, we finished our first course having answered the question, are wireless vibration sensors suitable for safety shutdowns? And after considering wireless sensor technology in comparison to hardwired sensors, we came to the conclusion that no, wireless sensors are not the best solution for shutting down your assets in the event of a breakdown or unsafe condition. Hardwired sensors, on the other hand, offer constant monitoring, high reliability, and simple to understand alarms, making this kind of technology much more ideal for protecting your personnel and assets from an unsafe environment. But what if you want more than just a safety alarm shutdown? What if you're looking to get more performance out of your vibration monitoring system, but you don't have a huge budget? So that's exactly what we're going to be addressing in this course. How can we optimize the performance of our vibration monitoring equipment without breaking the bank? And what are our options, and how can we overcome some installation challenges? And so that's what I'll cover today. And as always, the information in these courses is intended for educational purposes. So I've been careful to remove manufacturer-specific specs and promotional content. However, some of the resources have been provided by manufacturers we represent, so you may find a picture here or there to help with visualization. So along the way today, we're going to look at some early detection technology. So specifically, we're going to focus on FFTs and FFT alarms, and then we'll dive in a little bit into how can we perform an evaluation between different types of machines by looking at performance objectives. And then we'll move on to a budget example. How do we set our budget for maintenance equipment? That's always a tough question. And then let's identify some different trade-offs between types of equipment while we're setting a budget. We'll move into another example of expanding value or broadening the objective, where we can potentially use our vibration monitoring system to do more than just achieve vibration monitoring. We might be able to check off some important goals for our facility with the same equipment. And then lastly, we're going to look at some options that we've experienced here at Neil Systems. Some of our experience has allowed us to come up with some different ways of getting around retrofit challenges that might be common out there in the industry. So, and then when we're done, we'll be able to combine benefits of multiple systems to really check off all the boxes and still keep our budget in check. And so last presentation, I finished with this slide, and so we'll start here. And this is a slide that's going to be familiar to anybody in maintenance. It's the PF curve, or the interval between potential failure and functional failure. And so as the machine condition declines, that's this black line here, eventually what's going to happen is some sort of damage is going to initiate or start to occur. And as that damage progresses, the machine condition is continuing to decline. Eventually, we're going to get to a point where we experience a functional failure. Now the machine is no longer able to perform its designed task. And so before that initial damage starts to occur, if we're able to perform maintenance that will catch and prevent that damage from happening, I'm calling that proactive maintenance. And sometimes you might refer to it as predictive or condition-based maintenance, but for this presentation, we'll call this zone proactive. And then after that damage starts to occur and the machine condition's declining a little bit faster, depending on the mode of failure, the machine could decline faster or slower. But after that damage occurs, we're going to call that corrective maintenance, when we're working to correct the problem and restore the machine to its previous condition. And then once the machine reaches a point where it's no longer able to perform its function and we're essentially in emergency mode, I'm calling that reactive maintenance. And so you can see the cost of repair goes up for each of these different zones. And what we talked about in the last presentation, in the first part, was how level alarms can pretty consistently, for a wide range of failure modes, give us the ability to catch issues before they reach the point of functional failure. And so that puts us in the corrective zone most of the time with level alarms for vibration monitoring. But what if we want to be in the proactive zone? Can we use vibration monitoring to get into that proactive zone? So to do that, I'm going to cover this technology called FFT analysis as first step. So here's a cool picture I found, and I've referenced the website down at the bottom there. It's a really educational website, and I definitely recommend checking it out. But we've got this complex waveform over here, and this is what you're going to see. It's either maybe acceleration or velocity in time, and the red thick line travels in time, and it's this complex sinusoid that's actually combining several different sinusoids. And as an example, we've got them laid out here. There's this slower frequency sinusoid that has a little bit higher of an amplitude. And then here's a higher frequency sinusoid, slightly lower amplitude. And then over here, we've got this third sinusoid, which is higher frequency still and lower amplitude. And so as they combine and add together, they form this complex waveform that we're actually able to measure. So when we consider FFT technology, what we're doing is we're no longer looking at time as our x-axis, right? So this is what we're used to seeing as our x-axis on plots. We're going to transition to a different domain or different axis, and we're going to use frequency in this case. And so when we look at an FFT spectrum, what we're looking at is this thick black line where at the frequency of that first sinusoid that was combined, or the first component that was added into this complex vibration that we measured, we can actually use an FFT to look at its frequency on the x-axis and its amplitude on the y-axis. So the next sinusoid is going to have a different frequency. It's going to be located over here, and it's going to have this amplitude that's a little bit shorter than the first amplitude, and correspondingly the last one is exactly where you expect. So this thick dark line is what we would envision looking at for an FFT plot. And so what can that give us? Let me give you a quick example real quick here, where we've got an accelerometer, or it might be, in this case, we're taking the accelerometer and we're converting it into vibration data, and this is our raw vibration signal example that I've made up. And one thing we can do with it is, from our previous presentation, we looked at converting that raw signal into a level. And so maybe we're looking at an RMS level of velocity, and we're using that signal to generate that level. And right now we're measuring 0.15 inches per second, and that's on our 4 to 20 level, right? Or we could take that same data and look at its FFT spectrum, and here we might see some low amplitude, broad spectrum noise, right? It's not just sitting on zero. There's going to be some level of noise across the whole spectrum, but we've got two really clear peaks. One's at 1x on the frequency, and the other's at 2x on the frequency. 1x represents vibration frequencies that are the same frequency as the running speed. So if the shaft is spinning at 1800 RPM, then the 1x would correspond to an 1800 CPM or 30 hertz frequency, and the 2x likewise would correspond to 3600 CPM or 60 hertz frequency. So then what happens when we get a machine fault? In this example, I'm showing how in some cases, and this is true for a number of different vibration failure modes, but in some cases we can actually see a decline initially in the overall level of vibration as things change inside the machine. And so one of these conditions might look something like this, where that initial first bump on our FFT spectrum is actually shortened a little bit. It's still a 1x bump, and then maybe the same with the second, whereas our overall vibration noise level is increasing a bit, and we're seeing this hump that didn't exist before in the higher frequency ranges. And so if we had set our level alarms up here in the light blue dashed lines, if we had set our level alarms, we wouldn't have noticed this, right? Because we wouldn't have anything to tell us that the overall level dropped from 0.15 to 0.14. That's sort of a pretty insignificant overall change. But what we would have noticed is if we had our alarm set up so that anything unusual, right, would go outside of this custom alarm band that I've drawn here, that hump in the high frequency ranges might have alerted us to the fact that there's something going on. And this happens to be a pretty classic FFT signature for an early signs of bearing lubrication problems, right? So if something like this were to happen and we were to see it and get alerted to it, we might know immediately what to do. And before we're allowing this condition to get worse, we might be able to go and have our maintenance tech redo the lubrication, replace the oil, whatever needs to be done. And that could prevent us from allowing the fault to get worse and the machine condition to decline, because eventually what would happen is we would see the vibration levels increase on the overall level, on our overall levels. And that would probably put us over here where we're catching it where we expect to, in the corrective zone. But with FFTs, in some cases, the signatures will help us to identify problems and correct them while we're still in that proactive zone. And so if we can catch maintenance problems early, we have so many benefits, including better ability to schedule maintenance, which makes the whole thing, the whole process go smoother and less costly for our facilities. So let's look at a few different spectrum signatures that are common. The first one is called unbalanced, and it's the simplest to diagnose. It's characterized by this single hump here, or the single spike at the 1x frequency. And unbalance is really just the centrifugal force caused by mass that's not located at the geometric center of the shaft. And so as it spins around and around, it creates a sinusoid in the vibration that has the same frequency as the running speed. Misalignment is going to be similarly common to unbalance, because pretty much every machine is going to have some level of unbalance and misalignment. And so with misalignment, you're seeing the two shafts, or the driving, maybe the AC motor that's driving a pump or blower or a compressor, and the coupling's not perfectly aligned. What you're going to see, there could be an offset in the alignment. There could be parallel misalignment where the shaft center lines don't intersect, or there could be an angular misalignment where the shaft center lines are coming together at an angle. That angle could be at the bearing, or it could be at the coupling. And so there's usually some combination of different types of misalignment that are going to be combining into forming this vibration that we're measuring. But misalignment is oftentimes characterized by 1x, 2x, and 3x vibrations, and they can be a little bit different if you're measuring axial vibration versus radial vibration. So we also want to look at structural looseness up here. And structural looseness is interesting because looseness doesn't actually cause vibration. What looseness does is it amplifies already existing vibration. But so for instance, if you have a machine with zero vibration and you unscrewed the feet of the machine, it wouldn't move, right? Because there's no vibration for it there already. But let's say you've got a loose foot in a machine structure that has a 1x balance vibration that already exists. You may increase the 1x vibration. Also, you might create this 2x vibration as the machine rocks back and forth inside of that loose connection. Then there's another problem that's interesting to look at, and in FFT spectrum signatures, you can see for either clearance problems with the impeller or the rotor, and if there's maybe housing distortion caused by stress from the pipes or the mount or something like that, you can sometimes see this VPF frequency, which is the vane pass frequency, or sometimes it's called the blade pass frequency, and that's the number of vanes or blades on the impeller multiplied by the shaft speed. And so that's a common one to look out for as well. And these are all typically considered low frequency modes of vibration. So some mid-frequency modes of vibration include, up here we've got turbulence and cavitation. So turbulence and cavitation will often come with that same vane pass frequency that we saw earlier, as well as a bit of broadband noise that can occur in some of the higher frequencies. And then hydraulic wear, where you're getting bad clearances and in your asset, and maybe some recirculation is typically going to be associated with that same higher vane pass frequency peak, plus maybe multiples or harmonics of that vane pass frequency. And so we can also look at some AC motor problems as well. And one of the easiest AC motor problems to diagnose with vibration is a cracked motor. And that's going to occur at multiples of the running speed. But what's really interesting is with AC vibration, just like with balance in the physical vibration, when we're getting into electrical or vibration that's caused by an electrically driven motor unit, we're usually going to see this 2 times line frequency showing up in our curve. And so that's due to the air gap changes as the rotor spins within the stator. And since you're never really going to have perfect air gap all the way around, you're likely to see this 2 times line frequency vibration show up in a lot of different AC motor problems and issues. And so some 2x LF frequency vibrations could be normal, and then if it gets too high, that's when you want to be careful. And so cracked motor could look like this with these side bands at the 1x, 2x, and 3x, but then you're also going to see that 2x LF vibration as well. We can also try to look out for that uneven air gap on its own. And when we get into higher frequency vibrations, we can detect things like bearing looseness, because within a bearing, if you've got something moving around or banging against the edges, whether it's a sleeve bearing or a roller bearing, what you're going to end up doing is creating, instead of these rounds, sinusoid curves in the vibration data, you're going to kind of square those off. And when you square off those curves, you're going to create harmonics in the FFTs. And so sometimes bearing looseness can look like this top left plot up here. And then early bearing wear over here on the right oftentimes looks like that broad spectrum haystack is what they call it, hump in the higher frequency ranges. But there's also something that's usually associated with bearing defect frequencies, so spikes at specific frequencies that are associated with that bearing. It might be an outer race frequency or an inner race frequency or a ball element frequency. And that's the frequency that as the shaft spins around one time, there's a multiple of that frequency that will characterize how often an outer race would, if an outer race had a defect, how often a bearing would go over that defect. Or if a roller bearing had a defect, how often it turned over as the shaft spins around. And so you get these specific frequency spikes tend to be in the higher ranges. And then an interesting one to look at for back to AC motors is loose windings, and it's really high frequency, greater than 40x vibration. You'll sometimes see these humps with side bands in the vibrations FFT, and they'll be grouped specifically at 2 times that line frequency. So multiples of that 2 times that line frequency apart, and they'll occur separated like this. And then the other thing that we don't want to be confused, you don't want to confuse these with gear mesh problems, because they can look very similar. If you get a 1 times the gear mesh frequency, which is the shaft speed multiplied by the number of gear teeth, you can get this gear mesh frequency problem, and multiples of that gear mesh frequency problem will oftentimes show up if you have issues in your gears. And then again, you get those same side bands, but typically these aren't going to be separated by the same each time. Whereas when you look at the groupings that are multiples of this 2x line frequency. Anyway, the point is there's a lot that we can learn from looking at the FFT spectrums, right? And sometimes it takes an expert, because all this stuff can kind of interact with the different problems. They can sort of interact with each other and become complicated and difficult to understand and interpret. But we can gain something really, really important by looking at the FFT spectrums, right? And what that is so let's take an example of this FFT plot. Maybe this is our machine that's running at normal condition. So it's got a little bit of 1x vibration, a little bit of 2x vibration, and we see a small hump at the vane pass frequency. Well, if we're pretty comfortable with this as being a normal running speed condition, we can actually set low, mid, and high frequency alarms separately. And if we tailor our alarms to our machine, usually what we're going to do is have our mid threshold lower than our low threshold and our high threshold lower than that. What we can do is we can be ready to catch any changes that happen in the FFT. And if we're doing that, what we then have is the ability to detect early a wide range of different failure modes that might occur inside of our assets. And so by using FFTs and specific alarms that the FFTs can give us, we can actually achieve our goal of proactive maintenance using the FFT technology. So let's step back here for a second and take a look at how do we compare different vibration systems and monitoring equipment to each other. And one thing that I'm going to recommend here is that basically, most facilities, if you're in maintenance, you're familiar with this FMEA analysis table. Look at your asset, go, pull out these FMEA analysis that you did a long time ago, and set up another table next to it with categories for proactive, corrective, and safety, or maybe your plant might have different categories. And in order to compare different vibration equipment from different manufacturers, maybe you could go through and mark checks and X's on the different ways that each type of equipment is going to be able to help you find and avoid different modes of failure, right? So for each mode of failure, are you able to catch it proactively? Are you able to catch it correctively? And are you able to catch it before it becomes a safety problem? So that's a good way for us to compare different equipment. So now let's look at, change gears a little bit and look at setting up a budget. How do you talk about setting up a budget for a vibration or maintenance system? So the first thing we want to consider when we're talking about budgeting is actually what is the cost of unplanned downtime? And this is definitely a topic that's been addressed before, but I wanted to use this as a quick example so that we can form a framework for the rest of the presentation. But the biggest kind of contribution to the cost of unplanned downtime is going to be production loss. And so we're going to multiply the units of production, the things that we're producing or pumping or compressed air, how much flow we're getting, or for a blower, whatever it might be, or maybe it's hours of cooling that we're looking at. So what is our units of production multiplied or divided by per hour? And then we're going to multiply that by the unit value and then the number of hours that we're running. So the next contribution to cost of downtime would be employee productivity, right? Because if you've got an emergency going on, then people who are supposed to be doing something else are now focused on this emergency, or maybe they can't do their normal work because the emergency is preventing them from getting that done. And then the next is, we can quantify the cost of replacing equipment. And when you're in an emergency, you're oftentimes paying for expedite fees, contractor installation fees are going to be a significant part of that. And then obviously the replacement part costs themselves. And finally, the part we can't quantify is there's definitely an intangible cost having unplanned downtime. And so that's often going to be the relationship with the customer. So let's say you're producing something for a customer and you can't meet their demands. That's going to cause a problem. There's also the possibility that you lose an opportunity to grow or take on a new customer simply because you're supposed to be operating at 75% capacity. But with so much down equipment and having unplanned downtime, you're actually making most of your machines run at 100% and you're unable to take on more business. And then the last one that I listed here is that there's a morale concern that comes with unplanned downtime. So let's look at an example with a pump. Let's say this is a 600 horsepower pump, so pretty big. It's flowing 800,000 gallons per hour of water. And this is a water treatment facility, and they're able to charge $6 per 1,000 gallons, or 1/6 of a cent per gallon. And then let's just say, for instance, this pump is running 24 hours a day. This pump would be responsible for $115,000 of productivity. Sounds like a big number, but it's actually very common in a lot of these assets that we're looking at. $115,000 per day productivity is probably right in the middle of the ballpark. I've seen certainly as high as $500,000 a day, and then could be lower for sure. But there's also employee productivity issues that we have to be worried about, right? So let's say four employees, some of them engineers, some office workers not able to do what they're doing, and they're working shifts. So average that out, multiplied by 24 hours, and you've got close to $5,000 of employee productivity that you're losing. And then let's say in this case, it's not that, we didn't destroy this huge pump, and so we're able to fix maybe a bearing or get a new rotor in and have a contractor come out and do the installation. And maybe let's say we can get that done for $10,000. We'll go easy on that one. And then there's this intangibles that we can't really add in, right? But we know they're there. And so we're going to call this one $130,000 per day of cost for unplanned downtime. So conservatively, if we're in the proactive maintenance zone, we can expect, at least this is what Neil Systems generally recommends based on experience and some training from our manufacturers and customers, is that we would expect to save at least 1 day of unplanned downtime in 3 years for an asset if we're using proactive maintenance. And so if we then divide the cost of that downtime by 3, we're looking at our yearly cost of expected downtime, right? So now we've got essentially a yearly budget. If we're spending $43,000 a year on proactive maintenance, then we're really just breaking even. We're not having any benefit. But what if we only had to spend that $43,000 one time? And so let's put our budget at $43,000 for this equipment. And now we're suggesting to our boss or stakeholders, upper management, that $43,000 invested now will save $130,000 at some point in the next 3 years. That's actually a good business plan. And so what are our options for equipment? We've got 3 different categories for options of equipment here. And the first category is very appealing. It's going to typically check off all of our boxes. We're calling this the rack-based online system. And usually there's a rack involved. It's going to accept and sample data from a bunch of sensors on the equipment. And let's say for our pump and motor unit, the number of sensors and the equipment that we're going to need and the licenses to run the software are probably going to run us around 50 to 60K without installation. So unfortunately, right at the beginning, without even installation, we're over our budget. And so this is not an option for us in this case, based on the parameters that we've set out for ourselves. So that leaves us with 2 more categories of equipment. And if we look at wireless and cloud-based, we get this really awesome FFT technology that I was talking about, that we were discussing at the beginning, which puts us into that proactive zone, right? Where we're catching corrective issues, and we're even catching most of our proactive issues, maybe minus a few that we aren't sure we can get because we need some other sort of data input coming into the system, and we're going to catch those proactively. But we're going to do a really good job getting into the proactive zone with wireless equipment. However, wireless equipment is not designed, as we discussed in the previous presentation, to help us with safety needs. And so we're going to have to look at hardwired sensors for that. And between wireless systems and hardwired systems, we're typically going to run with wireless systems somewhere in the range of 15 to 20K, which could include the equipment, the installation, and the configuration. So you're in and out for somewhere in that range for a single asset. That's not uncharacteristic, and so or that's probably a pretty good range. I'm making estimates here, but I'm trying to be manufacturer neutral with those numbers. And with hardwired equipment, we actually have a bigger range depending on what type of hardwired equipment we're using. We're going to be somewhere in the range of maybe 5 to 20K for hardwired equipment, but then the install is going to be on top of that. And so depending on what we want, it's going to be very difficult for us to combine wireless and hardwired initially based on these, on these initial numbers within our budget. So let's see what we can do. So the first thing that I would suggest doing, and this is an interesting example from the past that we did, is we're going to try to get creative and broaden the objective a little bit. And so a lot of times with these wireless systems and wireless sensors, the gateway is a lot more powerful than just vibration. And so for this one specific vendor that we have, we could bring in just about any type of data that we want. We have industrial, I/O inputs and outputs with 420s, some limited industrial I/O that we can bring in, but we have the ability to bring in Modbus. So if we can get some plant data into this thing, not only can we monitor vibration, we can monitor pressure, flow, density. We can bring in motor current, motor voltage, bearing temperature, oil analysis reports, or maybe oil clarity levels, or even ultrasound data, right? And so now, with our ability to bring in all this data, we can create some really interesting custom dashboards where we're looking at not only vibration, but we're also considering process conditions at the same time. And so sometimes vibration is going to depend on the process conditions, and knowing the process conditions gives us greater insight, the ability to capture more modes of vibration early. And the really interesting thing here is In the upper right, we've got two interesting calculations we can do. We can do a pump efficiency calculation. In this picture, I didn't create this picture, but I'm aware that 89.5% pump efficiency is probably not realistic. But let's say we wanted to calculate pump efficiency. We could also calculate, let's say, for example, a health score of the equipment. And if we reach a certain threshold, that helps us make a decision. So what kind of decision could that be based on? Well, if we can calculate efficiency using pressure or flow combined with, so the power output, we can bring in the power input with motor amps and voltage. What if we could even bring in performance curves? So what if we digitize the pump performance curves or the asset performance curves that were given? We could calculate the efficiency that we'd expect the machine to run at. And with our calculated actual, the measured efficiency that we're measuring, we can calculate an efficiency loss value, right? So now we're tracking the efficiency of the machine and how much efficiency we've lost compared to its new condition, right? And so that's giving us a little bit more information to try to catch try to catch changes in the machine condition. But more importantly, what that also gives us, if we know how much we're paying for energy to run this machine, we can calculate operational costs or operational cost savings if we're able to gain that efficiency back. So now, when you go to do maintenance on your asset, and you're restoring the tolerances and you're replacing bearings and seals and getting your machine running back in the condition that it's designed or intended to run in when you bought it, you're not only preventing a breakdown, what you're doing is you're restoring efficiency and you're saving the company a lot of money. So let's take, for instance, that 600 horsepower pump we were talking about. At 600 horsepower, if we're running that thing 24 hours a day for a year, we're actually paying $400,000 per year to run. So imagine how much a few points of efficiency can actually gain us with that kind of money and runtime. Right? And so if you're able to bring this kind of information to the stakeholders, to your boss, to whoever's there in the company, you might be able to check off some important goals that the company has for achieving operational performance goals, right, and metrics. And so if we can bring something more than just vibration levels and FFT charts, we can sometimes expand our budget. So that might be one option, is expanding our budget. But let's look at some cost-saving alternatives that we've run into for specific retrofit examples. And so let's say you've got an asset out in the field and you want to do a retrofit. A lot of times what you're going to end up with is some existing conductors, right? Because with vibration installations, that when we talked about the hardwired systems, installation was such a big percentage of the cost. We want to look at trying to reuse any existing conductors that we can to avoid adding extra installation costs. And so, maybe existing conductors aren't in good shape or we can't use them, that's okay, but maybe they are. Maybe we can test them, confirm that existing, those conductors that are already out in the field are going to be useful. And so what we recommend initially is to take, maybe install some 2-wire transmitters and make use of the existing conductors to check off your safety box first, right? And so hopefully what that can do is that we can revisit this machine category slide that I showed earlier. And now instead of having a 20K installation, maybe we can take off a significant chunk of that and work toward reaching our budget for both systems instead of just the one. Right, so here's some other ideas about getting creative. Let's say you don't have enough existing conductors or you don't have any existing conductors. Something you can do is you can actually put a local monitor out in the field near your asset. And that way the installation is only going to this local box with a monitor on it. And then the monitor can communicate via Ethernet back to the control room, and that's going to reduce the installation burden. And so this might be another alternative way to reduce the cost, right? So if you can add a device that doesn't cost as much as the money you're saving on installation, then maybe you're working your way toward getting to a solution. And these local monitors can be invaluable in terms of providing. They can provide trending, and they can even do some alarming. locally and even send some of those alarms back to the control room. And that might actually help you get closer to your goal, right? So, these are just different ways of getting creative. And then, so far, what we've done basically is we've added these transmitters. So we've checked off our safety boxes, and now a good number of our corrective boxes, right? But maybe we can try to figure out a way to get some of those proactive boxes checked off. And so the good news is with wireless, when you're installing a wireless system, there really is no installation that you have to worry about. The only thing you're going to need to do is get the sensors mounted on the machine, which are in many cases magnetic, or epoxy, which is cheap and easy to do, and get power to that gateway. And then what we were talking about earlier is if we can bring process data into the gateway and solve some additional problems, we can check off more boxes on our proactive list, right? So now we're getting closer and closer to combining the solutions into exactly what we're looking for until we get, based on your facility needs and what your goals are, what your FMEA analysis tells you is important. There's probably some combination of equipment that will allow you to check off all the boxes you need. I mean, it always seems like we're stuck with not enough money to get the things done that we need. But if we use enough creativity and we can talk to what Mill Systems is working with a lot of different companies. And so we have experience to be able to tell you, hey, in this situation, we've done this before. We'd love to work with you to help you get your, help you get a setup, a vibration monitoring system that meets your goals, where you have down here your value, what you're getting out of it, what your company needs is more than your budget, which is more than the cost, right? So that's what we're trying to get to at the end of the day. And a lot of times by combining cloud wireless systems with hardwired levels, we're able to go ahead and look at the trade-offs, right? So the wireless system is not giving you safety, but it is giving you a lot of your proactive needs. And then the hardwired system is giving you safety, right? And then by combining the wireless and the hardwired system and bringing in process data, a lot of times what we can do is we can check off all the boxes that help your company get exactly what you need done. And so we're combining advantages to add value with a little bit broader scope in some cases. And so that wraps it up. Thanks again for joining this presentation of Wireless Essentials Part 2 through the Impact Training Center at Mill Systems.